My name is Michel Ferreira. In the previous talks in this session, we saw that mobility in smart cities is important. This talk will talk about one aspect which is often overlooked, which is the parking or the immobility of vehicles in a smart city. So some motivation. Parking is the single biggest land use in every city. So people don't realize immediately, but there's a lot of subsidization put into parking. So 90% of parking is free. We don't pay for parking, but it doesn't mean that it doesn't cost. In fact, free parking is estimated to cost as much as Medicare or national defense in the US. In this picture, this is downtown Atlanta, and the red boxes highlight areas that are fully devoted to parking. And they comprise 21% of the area in that part of the city. So if we can reduce this, say, to half or 1/3, then the impact on the landscape of our cities would be very, very significant. There's also another phenomenon associated with parking, which is not so relevant to what I will present here, which is the fact that cruising for parking can represent as much as 30% of traffic congestion. So one of the few people that has been looking very much into the problems of parking is Professor Donald Shoop. And regarding this 30% of traffic congestion, he says that a surprising amount of traffic is not caused by people who are on their way somewhere, rather it is caused by people who have already arrived. So if we can also simplify parking in terms of space, as I will present next, then we are also able to reduce this traffic congestion because it will be easier to find a parking place. More relevant to this talk is the other comment that Professor Shoop makes, which is that it is unfair to have cities where parking is free for cars and housing is expensive for people. Okay, so what we understood is that the current parking is not space efficient, and I think this picture shows clearly why. So this is scaled correctly. I have a Smart 2 and a Hummer H2 in parking spaces that are represented using the common size used in Europe. And the problem I think that you all understand is that as parking space is finite, but it should also be unbounded. So if we put those bounds in each parking space, then we make a Smart 2 occupy exactly the same space as a Hummer H2. And so if we want to solve the space efficiency of current parking, then we clearly have to solve this bounded design. So what we are aiming is represented in this picture. So on frame A, I represent a conventional parking lot. And this design will be important in the evaluation I will present later. So we have that design for a conventional parking lot that can hold 40 vehicles. Note that the bounded spaces are fully occupied by the Hummer H2, and they are also fully occupied by the Smart 2. But in terms of the density, clearly it is not optimal. And what we are aiming is really the frame B and frame C configurations. So frame B has roughly 1/3 of the area of frame A, while frame C has 1/5 of the area of frame A. So imagine that you could park cars in 1/5 of the space that they currently occupy, and you can understand the significance of that on the landscape of the city. So here the problem is that if you have a blocked car in frame B or C, then you will have to move the other cars so that yours can be extracted. And it is the optimization of this mobility that constitutes an interesting challenging from the point of view of automated planning and scheduling. So this, and I do mainly research in intelligent transportation systems, and the challenging here is really not the technology to park cars like this. It is the challenge of doing that in a manner that minimizes the overall mobility of parking, of the parking lot for the parked cars. So, the key idea, which we baptized as self-automated parking lots, is to replace the paradigm of immobile parked cars by a paradigm of cooperative mobility to achieve high-density parking of cars. Minimal inter-vehicle spacing, there is not even space to open doors, and no access ways can more than double the number of cars parked in a parking lot. The short and discontinuous mobility of parked cars is very efficient with hybrid and electric vehicles. You understand that vehicles that will be parked will be moving at very slow speeds, doing very short maneuvers, but that is very highly efficient if we are talking about hybrid or electric cars that don't have start engines. The energy conversion of that mobility is very efficient. And there is the challenging planning and scheduling problem to minimize the overall mobility of parked cars. So we wanted to make it very clear that the challenging was not in materializing this. And so from the beginning, we wanted to build a small-scale physical model. We resorted to these very tiny cars that are controlled by Bluetooth or Wi-Fi from a smartphone app. And we wanted to actually build the parking lot and show that if we can do this with toy cars, then doing this with real cars would be much simpler. The problem is really how will we place initially a car so that we can minimize the overall mobility. So just so we resorted to these Zen wheels. So this is one of those. We bought 100 of those cars to build the physical model, and they are controlled from a smartphone app. Okay, but what I want also to make clear is that while we have been playing with these very small cars, you now already have production vehicles that are controlled from your smartphone in the same way. So this is a Mercedes E, and so I'm trying to convince the funding agencies that instead of working with 100 of these, we should be working with 100 of those, right? But so they extract the car using the smartphone app. This is a car that you can already buy. So really the challenging is not the technology to implement this, is the planning and scheduling problem. So given a parking lot layout and a set of vehicles with entry and exit times for their parking sessions, assign parking spaces that minimize the overall number of maneuvers and distance travel. Using the expected exit time allows placing vehicles so that we rarely need to move blocking vehicles. For parking lots that have regular users, and this is a very common thing, it also makes sense to optimize based on expected future entries of vehicles and their common parking session duration. So you might reserve a spot to a car that will probably come up in the next 10 minutes. So we used a data set comprising around 100,000 parking events during the year 2013 for a parking lot with a capacity of 100 vehicles. We consider 4 metrics which are important for us. So, of course, parking space per vehicle. This is really the one that we want to optimize. So we want to reduce this to as low as possible. But also relevant is the number of maneuvers, the travel distance, and the waiting time on departure. We implemented 2 planning and control strategies, small length stack and also a conditional order on arrival. The main result is presented there. So the conventional parking lot had an area of 2,250 square meters, and we were able to reduce that using the buffer area and the 100 parking spaces to half, okay, representing a 50% reduction. So the number of maneuvers. So what we want, so this is a work which is still preliminary in terms of the strategy that we are used to place cars. But what we want to understand from the beginning is if we can actually park cars like this, or if the overall mobility will be prohibitively high to do this. And so this, even with very simple strategies, our results already show that we can park cars like this, okay? So this is the number of maneuvers. Even in the worst cases, we are talking about less than 30 maneuvers. 30 would be a very high value, right? If the car had to start 30 times. But note that on average, we are talking about values that in some cases are below 5. The starting position is also relevant. I don't have time to discuss this, but you see that we can either place the car in the immediately free position or further push it down the stack on the parking lot, and this affects very much these metrics. Also, in terms of travel distance, the values are quite comfortable. Even in the worst possible cases, we are talking about 500 meters, okay, for a car in the parking lot. And we can compare that to the conventional parking lot, because in the conventional parking lot, cars also move, right, to extract from where they are parked to the gate. And we were surprised to see that, and this is the conventional parking lot, that in fact, in the parking lot we are proposing, they actually move less than in a conventional parking lot, because the parking lot is smaller, right? And only because it is smaller, it can result, even with initial strategies, in a overall mobility which is smaller. And finally, the waiting time on departure is also very reasonable, right? For the 2 strategies, we achieve similar values, and we are talking about less than 30 seconds so that the car is extracted for you. Okay, and I finished my talk. I can just play the video while I answer your questions.
Yes.
In the data you had, did you have an identifier for cars from day to day?
Yes.
You knew who they were?
We used the parking lot of the university, which was the data that was most available, and everyone uses a card to open the gate. That's the data that we used.
Because you anticipated arrivals.
Yeah.
Other questions? Yes, please.
So do you think there's scope for more sophisticated strategies for doing the parking?
Definitely. That's why we wanted to present this to this community. We think this is a very challenging and interesting problem that can have a lot of significance in the landscape of our cities, but I think we can still do a lot. Note that while the park is empty, we could even move cars to another stack, okay, without extracting it. So what's interesting in this problem is that everything is in the car. So it's a fully distributed system with a lot of possibilities. So to simplify the approach, we use this design and simplify the maneuvers that could be done. But when the parking is still being filled, you could already start arranging so that you wouldn't have to move many cars when they start to exit. So definitely there are a lot of strategies that can be tried. The data sets are also very rich. We are now working with a major parking operator in Portugal, and they have a huge amount of data sets with the identification of each car, entry times, exit times, the machine learning issues to derive the entry time for each car and predict the exit time of each car will also be an interesting challenge. So definitely, yes.
Is the data available?
We will. So this data set is already available, okay, and we will also make those available.
Yes.
Do we have to wait until we have the remote control cars, or is there something one can do right now because in this application you need to be able to remotely move the cars, right?
Right.
So is there some technologies that can be used right now?
So that's why I showed the Mercedes E-Class, because they already have that, right? And that's not the only brand that's doing that. So the remote control of cars is something that will start being common, and I think that the perfect application would be this, because the environment is controlled, is a confined space. I think this, in terms of the automation of mobility in cars, this is really the low-hanging fruit that no one is collecting, right?
Yeah.
Cars are parked 95% of the time. This is really what you should be optimizing.
I was wondering whether you thought there was scope for trying to use domain-dependent planners to actually solve these problems. I mean, the reason why I'm asking is because there's a benchmark planning tools analyzer, this plant accelerator, all these plants parked in racks, and you have to, it's very intricate problem like this, and then you have to get a plant to analyze in chamber, and that's the other thing. And so I was wondering, in particular, I think the issue to use them would be if you have to deal with a lot of geometric constraints when you have to deal with them.
Right. So we simplified geometric constraints here in order to make a first approach to the problem. And we use very simple maneuvers. In that video, cars only moved from one stack to a stack that was I think 5 positions either to the left or to the right, but there could be more geometric maneuvers that you could allow. Even the case that these cars are all the same, and that also simplifies in terms of geometric configurations that can be achieved. But different cars would have different turning radius, would have different widths. So there's a lot still to research in this problem.
Okay, thank you so much.
Okay, thank you.